So in part B.2, now we do the estimate the cost, estimate computing cost. Now we need to remember currently we are working on polynomial evaluation, but we use the brute force, the straightforward method, brute force, the one everybody knows, that method. How to estimate the cost? To describe the cost, computation cost here, okay? Computation cost, all right? So we use the number of additions and the number of multiplications to measure the cost. Yeah. So that we did last time, yeah. And then we count the number of additions. Yeah. We count. Yeah. Here the number of additions, we get the answer n additions. N additions. How to get this number? We use a technique. We use a counting technique. It's called counting by reference. Because when we count certain objects, when you do counting, you count certain objects, right? Yeah. Here, we count the number of plus signs, right? How to get the number of additions? We know each addition in our formula, we use one plus sign to represent one addition. So in a formula, you need to count the number of plus signs, then you get the number of additions, right? Yeah. But when we count the number of plus signs, we get a problem. So the problem is, look at here, dot, 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 right? In our formula, we have to skip many terms, yeah, because we need to use the abbreviation to write our formula. We cannot write out all the terms. But when we skip most of the middle terms, the terms in the middle, the problem is we cannot keep track of the plus signs, right? We cannot keep track of the plus signs. So we have that problem, okay? Yeah. Then here I introduced an effective counting technique called counting by reference. So here, to keep track of our data, plus sign, that's our data, we find another set of objects. So that's our reference objects. So we find a set of reference objects. Between original set of objects and our reference set of objects, there is one-to-one correspondence. Okay? First, we need to establish one-to-one correspondence between these two sets of objects. Okay? Here, look at the first plus sign, we associate it. Yeah, so here, there is, I should be very careful because one student join, I need to use this place. Otherwise, if I use that place, then, the software problem, everything freezes. I have to restart my PowerPoint slides. Yeah, so that's why I use that one. All right. First plus sign, we associate with the first subscript after it, not before it, before the plus sign. We don't look at it, okay? Everything before the plus sign, we ignore it, okay? Now, the first subscript after the first plus sign, we draw a line between these two objects. The first object plus sign, the first reference object, the subscript 1. So we get that one-to-one correspondence. Second plus sign, second subscript after the first plus sign, okay? Yeah, so second plus sign, subscript 2, and so on. So here I list that, okay? So then, all the way down to the end, the last plus sign, we connected to the last subscript n. But after that, when we need to count the number plus signs, we know we should get the same number as the number of subscripts, right? Subscript, one-to-one correspondence. Based on set theory, okay? So here, I use a set theory a little bit. So part of discrete math, set theory, okay? So the one-to-one correspondence would give you the same number of objects in these two sets, okay? Same number of objects in these two sets. Yeah. But when we look at the number of subscripts, it's easy to count, okay? Although you have ... you won't get lost. Why? Because you know they are consecutive integers, right? Consecutive integers, okay? Yeah. There is no missing number in that ... okay? Consecutive. From 1 through n, you know, you get n objects. Yeah. So this is the technique, counting by reference. Okay, all right. Yeah. So after I describe it, yeah, here, okay, yeah. So we get this, the strategy here. Yeah. Work on the easier parts first. Yeah. Because our goal, we need to count two operations, right? Additions and multiplication, these two operations. Yeah. When we work on more than one tasks, here we have two subtasks, right? Counting number of additions, task 1. Counting number of multiplications, task 2. So when we have more than one task, when we start, we should start with the easier one, okay? Do not start with harder one, okay? Easier one. You can always do better. Yeah. Here, the easier task, counting number of additions. That's easy. Yeah. So we just did it. Yeah. All right. The hard point, yeah, so here, yeah, I explained, so we couldn't keep track of the data, right? Yeah. So here, I just described this counting technique, counting by reference, okay? The essence of method, here I use a small program to explain. Yeah. After you find appropriate reference object, then you need to discover one-to-one correspondence. Yeah. All right, so here. Object 1, object 2. Object 1, usually harder to count. Okay? Yeah, usually hard to count. Why hard to count? It's hard to keep track of all the objects in the set. Yeah. Hard to keep track of. Due to the environment. Okay? Due to the environment, it's hard to keep track of the data. Yeah. But object 2, much easier to count. Okay? Yeah. But then you have one-to-one correspondence between object 1, object 2. One-to-one. Okay? Yeah, must be one-to-one. Yeah. All right. Object 1 plus sign, object 2, subscript. Okay? Yeah. All right. So then, after that, now you count the easier counting objects. Yeah. So you get an answer, you know, that answer, that's the same number for the object 1. Yeah. So here we use this method the first time. Okay? Yeah. Later, we will use this technique a few more times. Yeah. All right, so next thing. Yeah. Go back to estimating the cost. Yeah. After we get the number of n additions. Yeah. Remember, last time we did another thing. In order to make our total cost description containing two different operations, addition, multiplication, we need to make appropriate assumption to to put them in a fair playground, right? Fair playground. Yeah. And we know in the real world situation, response time for each multiplication is much slower than the response time for the addition. Yeah. The ratio approximately 10 to 1 ratio. Yeah. If we look at the computer hardware, if you get into the CPU, get inside CPU, yeah, approximately the response time for one multiplication is approximately 10 times of that of an addition. Yeah. Addition, the time used usually in nanosecond. So do you know how large is a nanosecond? 1 nanosecond, how large is it? Nanosecond, 1 nanosecond. How much of 1 second? Yeah, you use it. So 1 nanosecond equals how much of 1 second? Negative, oh yeah, very close, but not right. He said 10 to the negative 7. Any different number? Any different? 9. 9, okay? Yeah. 3, 6, 9, okay? 3, 6, 9. 3 millisecond, right? 1,000th of a second, so millisecond. Another 1,000 microsecond, okay? Another 1,000, so 1 millionth, that's 1 millionth, okay? Another 1,000th, another 1,000th, so 10 to the negative 9th, 1 billionth, 1 billionth, okay? Yeah, that's 1 nanosecond, right? One addition, it takes certain multiple of 1 nanosecond in that level, okay? So then, one multiplication approximately 10 times of that number, okay? Yeah, so here you get an idea. Yeah. All right, then, so we convert the number of n additions to number of time units. In our assumption, we assume one addition, we use 1 time unit, 1 unit of time, okay? So 10, then n additions here, we use n units of time, okay? The first part, addition part. Then let's move to the second part, multiplication part. How many units of time do we need to calculate all the multiplications in a polynomial evaluation? Okay, yeah. So our task number 2, okay, subproblem number 2, okay. Count the number of multiplications. Yeah. Yeah. Remember, we did partial work last time. Partial work for each term, we count the number of multiplications. So we can use that result. Okay, so we carry that result from last time. Okay, yeah. All right. When we calculate this term, this is a typical representative term, a sub k times x to the kth. Yeah. How many multiplications last time we got? Anyone still remember how many multiplications we got last time? K, yeah, all right? K, all right? Yeah. So then, this time, we only need to accumulate all the number of multiplications, combining all the terms, how many? Yeah. So we just do a summation. We do a summation, we can get, combining all n plus 1 terms. Yeah. The first term, no contribution, right? Well, starting from the second term, then we have each term there is a contribution, okay? Number of multiplication, contribution. Yeah. So here, I, do a chart, list number of multiplications for each term. Okay. Yeah. So the bottom line, the bottom row, yeah, So A1 term, A1 X term, 1 multiplication. Second term, next term, 2, 3, and so on. Yeah. Total number of multiplications, we add up all these n numbers. First consecutive positive integers. What's that formula? Anyone still remember? Last time I wrote on screen. Yeah. Yeah. But in your discrete method, we also learned this formula. Okay? Anyone still remember a little bit? This formula, very basic. You need to memorize it. Okay? Yeah. So for this class, we use this formula everywhere. All right? You need to memorize it. So what's the formula, anyone? Still remember? 1/2 times n plus 1. Good. Yeah. All right. But remember, this number gives us the number of multiplications. But we need to convert it to the number of units of time. Time units. Okay? How many time units do we need to calculate all the multiplications? All the multiplications. 10 times this formula, right? 10 times this formula. Yeah, all right. So that is, yeah, so we already have n additions, n units. Yeah, this many multiplications, we need to multiply by 10, okay? After multiply by 10, we get a 5n times n plus 1 units. Now total units, add up these two parts. That's the total cost. Total computation cost, yeah, for this question. So this number, the total computation cost to find the answer of this polynomial. Yeah. So can you see that? Yeah. All right. So we get an estimation of the cost. Estimation of the cost. Okay? All right. Yeah. So the next question. How to reduce this number? Our goal, we want to improve our algorithm. So every time after we find a solution, we want to think about, is it possible to improve this algorithm? Here, let's think about this question. Is it possible to get a better algorithm? That means the total number of time units should be smaller than this one, okay? Yeah, much smaller than this number. That's our next task, okay? Next task. All right, yeah. At this point, it's not easy, yeah, for you, yeah. All right, so our next task, how to reduce this number. Yeah. So here, let me give you another improvement strategy. Improvement strategy, okay? When we need to solve a new problem, and this problem is not easy to solve, okay? Not easy to solve. In this situation, usually, we need some strategy, okay? We need some strategy. So here, the improvement strategy. Yeah. All right. Think about in a real world situation. When we need to solve this kind of problem in the real world, all right? Yeah. Usually we have limited resource, right? Yeah. In the real, you do not have unlimited resource, right? Yeah. People always, you only have limited resource. When you have limited resource, where do you want to put your precious resource? In which part do you want to put your precious resource? Here we have two parts, addition part and a multiplication part. Yeah. But our resource is limited, okay? Yeah. Do you want to invest your resource in improving Do you want to invest your resource in the improving the addition part or improving the multiplication part? Two possible ways. Which part you want to put your precious resource?
How do you improve the multiplication part?
Correct. Yeah. Right. Exactly. So here you bring your intuition. Yeah. Why the reason? The reason is simple, right? Can you explain a little bit? What's the reason you want to?
No, it was more like a question, like how do we improve it?
Yeah.
How do we improve the multiplication part?
Oh, how? That's another question. All right.
Yeah.
How? That's another question. So here, first, let me go back to the previous slide. Look at this one. All right. Look at this. Right. In the total cost, among the total, this is the total cost, right? This is the total cost. Among the total cost, the contribution from the multiplication, this much. The contribution from addition, this much. Can you see the big difference? Can you see the big difference? Yeah. If you invest your resource in multiplication, will you have better chance to do bigger improvement? If you put your precious investment in the addition part, your improvement is very little. Right? Improvement is very little. That's the main point. Let me use a simple diagram to explain it. Okay? Yeah, let me draw a simple diagram. Suppose when we do computation of whole polynomial, this circle represents the total cost, total time, total execution time we used. Okay. And then let's look at the share for the multiplication and addition. The percentage, the share for the addition is very little, right? This much. The share for the multiplication, big part, okay? Yeah. But the way here we want to do reduction. We want to do computing time reduction. So do you want to reduce the number of multiplications or number of additions? Yeah. So here, based on our intuition, based on our real world experience, we have more room for the improvement in multiplication part. More room, okay? Yeah. So if we just improve this much, then this big part is the gain, right? This big part is the gain. But for addition part, you cannot get that much gain, right? Think about, yeah. So then, one computer scientist summarized this observation in a principle, in a rule, principle. It's called Amdahl's law. Amdahl's law, okay? Amdahl's law. So what's that? Yeah. So when you need to, put your resource solving a problem, you want to put your resource in the common task. Common task. What's the common? The task is more common. Common. That means, the percentage of the time used for that task is larger, is bigger. Okay, bigger percentage. Okay, that's the common task. So you put your resource in that common task. Amdahl's law. Okay. Question. Oh, so feel good, right? Okay, good. Yeah, that's the Amdahl's law. All right. Yeah. All right. So here, which part focus on? Yeah. 10-to-1 ratio, well, the difference so big, all right? Other than this unit difference, so each 1-to-1, that difference. In the formula part, also the big difference, okay? Yeah. So we should focus on the major part, not the minor part, okay? Minor part, you waste your resource, okay? Yeah. No matter how hard you try, your improvement is very, okay? All right, the conclusion. Focus more on multiplications. How to, that's another question. Okay? So we will answer that question. Next step, how to reduce the number of multiplications. Yeah. All right. Yeah. But we set our strategy, our direction, which direction to go. We want to reduce the number of multiplications. That's the direction to go. Okay? All right. The new question, how to reduce the multiplications. Yeah. That's the key problem to solve. If we can solve this problem, we will get a solution. Yeah, we will get a final solution quickly. Okay? All right. B.3, Horner's rule. Yeah. So this is the, very smart solution. Horner's rule. Okay? All right. Yeah. So let me. All right. Now, our current goal, so this is our current goal, okay? Reduce the number of multiplications. When we solve this problem, now, we know it's not easy to solve, okay? How to reduce number of multiplications, it's not easy, okay? So in this situation, we need another strategy. We need a strategy, okay? Yeah. So this time, strategy is study a simpler case. The strategy. Study simpler case. So this one, actually we did last time. Last time, we do experiments. Remember? Last time, when we count the number of multiplication for each term, how to get it? Then the strategy we mentioned at that time, do some experiments. Here we also do experiments. Okay? But when we do experiments, we want to work on simpler case. We don't want to work on difficult cases. Think about, do you want to work on a polynomial with 100 terms? That's a hard case, right? So we don't want to work on that big polynomial. Okay? Yeah. So usually we work on relatively simple cases. So here, so let's work on some. Yeah, we want to get some pattern, Yeah, when we do experiments, we do observations, right? So looking for some rules, patterns, some phenomenon, right? Yeah, things like that. Okay, all right. Yeah, so discover certain property from the experiments. So it is easier to do experiments when the data sizes are small. Okay? Yeah. Make our life easier. Okay? So you don't want to, if you work on polynomial with degree 10, it's not easy, right? Degree 10. Okay? That's not easy. Yeah. So we should choose a number degree much smaller than 10, even. Yeah. But another question, if the number is too small, you may not get useful information. Okay? So we want to start with a simpler case, but meaningful. The simpler case should also be meaningful. Okay? All right. Yeah. So let's look at all right. So here, let's do the work, okay? So let's consider degree 2 case, n equals 2, not n equals 1. If n equals 1, it may not be meaningful, right? Too simple, okay? Too simple, yeah. So now let's work on the first simple case, meaningful simple case, n equals 2. So we get a quadratic formula. Degree 2, quadratic. 3 terms. Now, you try do the observation on this polynomial. Can you see some interesting property there? Any interesting property? Yeah, do observation. Try to find some interesting property that could be useful in our multiplication calculation. Related. So this property should be related to the multiplication. Okay? Yeah. All right? Can you see it? Anything? There are three terms. Compare these three terms. Can you see some useful property related to multiplication? Yes, common factor. Common factor. But this common factor, you have to bypass the first term. Okay? Yeah. After you skip the first term, then you can see common factor. Then you can see common factors. You have to skip the first term. Okay? Yeah. All right. Yeah, first term A0. A0. Yeah. There is no common factor, right? For A0, no common factor. Yeah. But after you skip the first term, A0, then the remaining terms, you can find a common factor X. When you see a common factor, can you do some special operation on the common factor? Now, what do you usually do on a common factor? When you see a common factor, what do you usually do? Yes. Yeah. So we do factorization. We call it factorization. So you factor that common factor out. Okay? You factor your common factor out, the common factor X, factorization. Yeah. You factor out that common factor X. The remaining part inside parentheses, a pair of parentheses. Okay? All right. After that, yeah, look at this step. Look at this factorization step. What did we do in this factorization step? We did something, right? Yeah. We did a mathematical operation on our original formula by the factorization. Yeah. But this factorization operation does not change the result, right? Do we change the result of the polynomial, quadratic polynomial? No, we do not change. Okay? The same result. Okay? But the question, do we change the structure of this polynomial? Do we change the, the structure, the formula structure? We changed, right? The formula structure. The formula structure change would result in computation order change. Okay? When we do computation, if we use the new structure, do we need to use a different order of multiplication and addition? Yeah, we will use a different order of operations. Yeah. So then, an actual expectation, the number of multiplications could be different, right? We change the structure. If we change the structure, then it's natural we expect to get a different number of multiplications, right? Yeah. Let's do the counting this time. Let's do the counting. Okay? All right. Before we change the structure, the total number of multiplications, the first term 1, second term 2, 1 plus 2, 3, before we change the structure. After we change the structure, can you count the number of multiplication again? Do not count the number of addition, only number of multiplication. Can you count how many multiplications do we need? In the new structure, 2. Yeah, 2. Because between x and that pair of parentheses, there is between A2 and x inside parentheses, second one. So 1 plus 1, 2. So 1 is here, and 1 is here. 1 plus 1 is 2. In this way, you can see we have the multiplication reduction from 3 to 2. 3 multiplications, the older method, after we do the factorization, we have some gain. The gain for this small example, 1 multiplication reduction. That's pretty good. For a quadratic polynomial, you can reduce multiplication by 1. For higher degree, you should reduce more multiplications, right? You have chance to reduce more multiplications. Yeah. All right. So the summary. Yeah. What we just did. Yeah. Yeah. We changed the order of operations by factorization that results in better efficiency. Yeah. So here you can see the key to the success, that's the factorization. Why we can do the improvement? Because we take advantage of this factorization technique. Okay? That's the key to the success. All right. Can we generalize this idea to the general end? Yeah. So our goal, we need to generalize, because this is a special example. In order to solve the whole problem, you need to do the generalization on the general degree n. Yeah. So next, in order to do the generalization, we feel we need to, because we just did one experiment. We feel we need to do a little more experiment to get more experience. Okay? Yeah. So one experiment still, we observed some useful properties, but still not very strong. Okay? So we want to do another round experiment so that we can consolidate our understanding. Okay? Yeah. So our observation of the critical property. Okay? Yeah. So here, let's do another round experiment. This time, the degree n equals 3, so we work on a cubic polynomial. So here, it's a cubic polynomial. Okay? All right. Yeah. So based on so now you have some experience. Okay? Yeah. So based on your experience, what do you want to do? Factorization. But how do you do the factorization? Okay, tell me. Yeah. How do you do the factorization? That's the question. Based on your experience from previous example, how do you want to do the factorization? Think about. Similar way, but you need to do.
Like nest it, so you could take out. You can factor it partially.
Yeah.
So
Right.
you can remove x from the last 3 terms and keep a0 separate.
Yeah. Yeah. We can. We can. We can. What first?
Remove a first.
Oh, okay. Remove A0, right? Cross out this, right? Skip it. Then we do factorization, right? Good. That's the right way, okay? Yeah. Only skip the first term. Because after you skip the first term, you already have the common factor, right? When you have a common factor, then you factor it. Factor that common factor, right? Okay? Yeah? All right. So that's what we do. The key to the success, do factorization. Our decision, we take advantage of the factorization technique, okay? But when we do it, we want our factorization operation cover as many terms as possible. The more we cover, the better we can do. Okay? Yeah, because we know factorization, that's the main reason to reduce the number of multiplications. If we make our factorization coverage as large as possible, then our chance to reduce the multiplication will be bigger, right? So we want a bigger chance. So here, let's do the first round factorization. That's our first round factorization. Okay? Yeah, factor 1x out. Then we have a big pair of parentheses. This pair of parentheses cover 3 terms, right? Have 3 terms. Then, in the 3 terms covered by this pair of parentheses, do we have further chance to do factorization? Further chance to do some factorization?
The last 2 terms, you back up the x.
Yes, yes. We just skip. Yeah. The current first term, okay? Yeah. These are big parentheses. That's our current formula, okay? Current. Smaller polynomial. Yeah. The first one, we bypass it. Bypass it. Then we can do factorization on 2 terms. Another round. This is our second round factorization. Okay? Yeah. So then, because we know whenever we apply factorization, we can save certain number of multiplications, right? Yeah, we can save. So we try to apply factorization as many rounds as possible, okay? Until we cannot, right? Until we hit a point, we cannot do any factorization. So we stop, okay? Yeah. So now, so after that, how about we rewrite our original cubic polynomial in this structure, containing 2 rounds of factorization, like this. Okay? Yeah. Now, let's count the number of multiplications we can save in this restructured cubic polynomial. Okay? Before restructuring, how many multiplications do we need to calculate that cubic polynomial? How many? Do the counting. Do the counting. How many? How many? 1, 2, 3. Adding up. Adding up, right? 6. Before restructuring, you need 6 multiplications. After the restructuring, how many multiplications do you need?
6 for what?
6 multiplications, right? This term, 1 contribution. This term, 2 contributions. Okay? 3 contributions adding up equals 6 multiplications. Can you see that? Can you see that? 6 multiplications. Okay? All right.
So now you only need
5. What? Oh, the other one. Oh, now let's count the other one. Okay? Do not look at the addition. Okay? Do not look at the addition. Only multiplication. Only multiplication.
Is that because of x squared? You got 2 over there because it says x squared, like,
X squared 1 multiplication, right?
yeah, okay.
A2. We did last time. You know, the term with subscript k has k multiplications. The subscript 2, 2 multiplications. We did last time. Okay? All right? All right. Now, let's count the number of multiplications after restructuring. Okay? All right. First multiplication between x and the first pair of parentheses. First multiplication. Okay? All right. Second multiplication between second x and the second pair of parentheses. Second multiplication. Third, between A3 and x. Third multiplication. That's all we have, right? No other multiplications. Additions, bypass additions. So the total number of multiplication, 3. Look at the reduction. How big? From 6 to 3. From 6 to 3. That's the reduction for a cubic polynomial. Is that big? Right? Is this we only do a small experiment, but the result is very encouraging, right? Very encouraging. Do you want to keep going along this direction? Right? Yeah. So you want to along this direction and go to the general case, degree n case. We want to find a solution for degree n. We know this direction must be right. Yeah, it cannot be wrong. Right? So encouraging here. Okay? Yeah. So let's do the general case. Here you can see, let's do another small summary here. Yeah. The key to the success, the factorization, right? We know that's the main reason we can do this better. This good, okay? Yeah. Main reason. So it tells us when we have a chance to apply this factorization technique, we should apply it as much as possible. Okay? As much as possible.
It's a factorization?
Yeah, factorization. Okay? Yeah. Yeah. So that's, some experience we learned from this experiment. Yeah. Let's move to next step. Yeah. So we push this method to the general case. And we want to find a final solution for the general case. Yeah. The strategy for the general case. Okay. This time, we need to use another strategy. Okay? Yeah. So look at another strategy. So here you can see every step we need to apply some strategy. Okay? Yeah. So that's the typical problem solving. Every time when you have a relatively hard problem to solve, you need to think about what strategy to use. Here. Yep. In this situation, we still feel it's not that easy to do the generalization. Okay? Although we have a lot of experience, but still, we need to use some strategy. Yeah. So here the strategy is do factorization as much as we can. That's the strategy. Okay? Yeah. Very natural, because we know in our first 2 rounds of experiments, the key to the success is factorization. So now we want to basically doing the same way. Yeah. Yeah. All right. Yeah. As much as we can. So here, we need to understand this phrase. What do you mean as much as we can? This phrase here. Okay? Yeah. Here, let me introduce another well-known strategy in computer algorithms. Computer algorithm, there is a very important strategy here. So let me introduce that one here. It's called a greedy strategy. Greedy strategy. Yeah. So why people call greedy? Because here this phrase, as much as we can. That's something related to the greedy, right? Yeah. So we call this new strategy the greedy strategy. Okay? So here, the algorithm we are going to use, we call the greedy algorithm. Okay? So here we will apply the greedy algorithm to solve remaining part of the problem by the greedy algorithm. Yeah. So let me show you how to apply the greedy strategy here. Greedy algorithms. Let me give you the description of the greedy algorithms here. What's that? Apply some property as much as we can at each step. This part important. Yeah. So what do we mean at each step? All right. You know, when we solve a big problem, usually we need to split it into many steps, right? So we solve a big problem step by step. Step by step. So that's the usual way. Yeah. But when you apply the greedy strategy, greedy algorithm, greedy strategy, each step, you apply some property as much as you can in each step. So next step, apply greedy strategy as much as you can again, as much as you can again. Each step, as much as you can. So then, you put everything, all the steps together, you'll find a solution. This way, this approach, we call the greedy algorithms. Here, that's some property here, that's our factorization property. Our common factor property, okay? Common factor property, so we do factorization on it, okay? Yeah, all right. So here, but each step, we call our improvement, it's a local improvement. Because when we apply some property on each step, that's the local application, right? It's not global application. Yeah. So greedy strategy, you only solve the problem with local optimization. If you look at locally, it's optimal. Because that's the best you can do, right? So it's a local optimal solution. If you look at locally, it's optimal. But if you look at globally, it may not be optimal, okay? Globally, local optimal may not give you the global solution, optimal solution. That's another important property of the greedy algorithm. You may not get a globally optimal solution. Okay? Yeah. But you get a solution, and you have a chance. You have a chance to get a globally. If you're lucky, you get a globally optimal solution. But if you're lucky, okay? Yeah. If you're not lucky, you cannot get globally optimal solution. Yeah. So that's the greedy strategy. Okay? All right. So here, it may not be optimal because it could be very hard to get an optimal solution. Yeah. In order to get globally optimal solution, it could be very hard. Okay? Yeah. Sometimes impossible. Sometimes people in our generation, we do not know how to solve, how to get globally optimal solution. Okay? So we may need, our future generation to solve the problems. Yeah. So we cannot solve. There are many problems, open problems we cannot solve right now. Okay? Yeah? All right. So let's do the generalization on this general formula. And we apply the greedy strategy. Okay? All right. So after we skip the first term, we can do one factorization covering all the other terms. Okay? With this pattern. Yeah. With the pattern similar to what we have in a cubic polynomial, but we just write it degree n case, so you get this structure. Look at that. Okay? So you do factorization round by round. First round, second round, third round, and so on, all the way to the last round until you cannot proceed with further factorization. How about that? How about that process? Okay? So this is the greedy strategy. How we apply the greedy strategy here. Okay? So think about this greedy strategy. Yeah, yeah. Later in the remaining of the course, we will apply this greedy strategy a few more times. Okay? Yeah. Yeah. So here we learn it the first time. First time we learn the greedy strategy. Okay? Yeah. All right. So this is called Horner's rule. When you evaluate polynomial this way, if you calculate a polynomial in this way, That's called the Horner's rule. Okay. If I ask you to write a computer program to calculate a polynomial by Horner's rule, do you know how to write the code? Okay? How to implement it in a computer program? Question. Yes, yeah, recursion. Okay? Yeah. Recursion. Yeah. So that's our first programming project. Our first programming project. Okay? Yeah. So this weekend I can post our first programming project. Evaluate polynomial. We will use 3 methods. 3 methods. Okay? Yeah. Method 1, brute force. Yeah. Our first method, brute force. Okay? Yeah. Method 2, I will give you later. Method 2. Yeah. Actually, I showed you last time. Yeah. I showed you last time, but I need to talk about more about second method. Yeah. Method 3, Horner's rule. You need to compare these 3 methods. Which one is the fastest? Okay? And when we do the experiments, we want to work on large polynomials, very large polynomials. Okay? Yeah. All right. Yeah. How many multiplications are there based on the new formula? Can you do the counting? How many multiplications do we need here? Anyone? Based on you have learned. Yeah. So a lot of results we have learned so far. Can you get n? Yeah. Any other possible answers? N? Why n? Can anyone explain how you get n? Good. You by induction. Okay? When we have 2, we have 2. Well, when degree is 3, we get 3. So then, by induction, you get n. Okay? Yeah. So that's one way. But here, another place we can apply our counting technique, counting by reference, right? Each multiplication, can we associate with a different object, an easier counting object? This multiplication, the first one, can we associate with this subscript, A1? 1, the subscript. The second multiplication, can we associate with subscript 2 of A2? And so on, okay? Dot, dot, dot. This one, multiplication associated with the subscript. The last multiplication associated with the subscript. How about that? So all the number, we just count the number of subscripts. And we can keep track of all the subscripts, right? 1 through n. In that way, we get n. So practice this technique. Very effective, okay? Counting by reference. Very effective. Okay? Yeah. So here you know appropriate methods are important, right? At each step, if you apply appropriate method, then it's not hard. But if you do not know those methods, then you can see it's not easy. Okay? At this point, we have learned many methods. Many methods, okay? Yeah? Yeah. Think about that. Okay? All right. Yeah. All right. So the answer is M. Yeah. All right. Yeah, so I only have 10 minutes. Let me complete. B.4, visualize performance improvement. Yeah, the last step. How big is the improvement? We know we get pretty good improvement, right? Yeah. But can you get a concrete view of the improvement? How large is the improvement? Can you get that? How large is the improvement? Okay, so here I want to impress you. How large is the improvement? Yeah. impressed. Yeah. Yeah. All right. We see the difference in formula. Let's look at it, compare the formula difference. Yeah. Before the improvement, the number multiplication is this number, 1/2 times n minus 1. Okay? Yeah, so we copy the number of multiplications from our previous slides. Yeah, this number. After the improvement factorization, Horner's rule, we get n multiplications. Do you know how large is the difference between these two expressions? Quadratic polynomial, right? Degree 2 polynomial. The second expression, n, it's a linear polynomial. So you know, visually, they are different in math formulas. But the question is, we want to really feel about it. How big is the difference? We want to feel about it. Okay? So here I want to use some visual way to let you feel about it. How big is the difference? Yeah. So let me do some experiments. So let's do some more experiments here. Okay, all right. Yeah. Impact of multiplication reduction. Yeah. All right. How big is that? It is too abstract to feel about the difference. Yeah. If you only look at from the formula, very abstract. Okay? Yeah. So you don't have concrete numbers. So you feel it's very abstract. In order to get a good feel, we need concrete numbers. Yeah. So let's try out a couple examples here. The first example, we choose n equals 1,000. So we want to calculate a polynomial with degree 1,000 using these two methods. The first one, the brute force method. The second one, the Horner's rule method. If you apply the first method, how many multiplications do you need? The first method. Let's plug in, right? N equals 1,000. Let's plug in into the first formula. Okay? Yeah. Here, we do some good approximation, yeah, because so there is some minor part. We just keep the major part, okay? Yeah? Yeah. So here, the major part, 500 million. We get approximately 500 million multiplications. Yeah. Because 1,000 here, 1,000 here, 1,001, right? 1,001 we replace by 1,000. Slightly smaller, because 1,000 divided by 2, 500, that's easier to calculate, right? Yeah. So we do not keep the fraction part, okay? Yeah. So here, we use a good approximation number, 500,000 multiplications versus 1,000 multiplication. How large is the difference? Yeah. If you compare our first example, the difference is 500 to 1 ratio. 500 to 1 ratio. Is it good improvement? Okay. If you use the first method, the amount of time, you use certain amount of time, but the second method, you only need 1/500th. You only need to use the amount of time that is 1/500th of the time you use in the first method. Is a big improvement? Huge improvement? Yeah? The percentage, okay? 0.2%. Your time you use is 0.2%. Less than 1%. 0.2%. How good is that, right? Yeah? But that's for degree. N equals 1,000. This time, I want to try another example with 1 million degree. Yeah. Because right now we are in a big data era. It's possible we need to do large computation like this, okay? with a polynomial degree 1 million. Okay? You need to find the result as fast as you can. Okay? If you apply the brute force method, how much time? How many multiplications you need? Let's plug in n equals 1 million. Yeah. Yeah. Can you, we get an estimate number. Can you read out what's this big number? Other tries. How large is this number? Oh, good. Yeah, 500 billion. You're correct. Okay? Yeah, you're correct. Yeah. Okay? 500 billion. Yeah, 500 billion. Okay? What's the ratio between these two numbers? What's the ratio between these two numbers? Correct. 500 to 1 ratio. Do you know how big is that? Yeah? How big is that? The first method, second method, the second method, you need 1/500th amount of time used in the first method. How big is that? Okay? All right. Here, because if you look at 500 times versus 1, you cannot feel how much better it is. So here, let me use another conversion to let you feel better about the difference. Let's make that 1 corresponds to 1 second. How about that? This 1 here refers to 1 second. Okay? So we need 1 second. If you apply Horner's rule, we use 1 second. We can find the answer of the 1 million degree polynomial. But then, the 500 seconds, do you know how long is 500,000 seconds? 500,000 seconds. Let me convert it to number of days to show how long. Okay. 5.8 days. Approximately 5.8 days. Now you see the big difference. If given a polynomial, 1 million degree polynomial, if you apply the Horner's rule, you just need 1 second. You hit the enter key. After 1 second, you see the answer display on the screen. Okay? Then, if you use our brute force method, after you hit enter key, you need to wait 5.8 days to get answer. Okay? That's the huge difference. Can you see that? Can you see that huge difference? You need to wait 5.8 days, okay, to get an answer. Okay? Yeah. Think about if you provide business solutions to your customers. Business solutions to your customers. You don't want to ask your customers to wait 5.8 days to get a result, right? Yeah. So you want this 1 second solution, right? Not 5.8 day solution, right? Yeah. So this experiment, you'll see the huge difference in good algorithm and a bad algorithm versus bad algorithm. The huge difference, okay? Yeah, so that's the reason we learned this class, okay? So we want to do that 1 second solution, okay? Not 5.8 days solution, okay? All right, that's it. Yeah. So we finished part B. Yeah. Next time we will start part C. This weekend, I will post our exercise question set number 1, covering part A and part B. Exercise questions, that's for your self-study. You do not need to turn in. For your self-study. And I will post the answers later. This